Hello, and welcome to today's lesson. We're moving on to our Circles and Polygons Unit 3, Lesson 1. Okay, our essential learnings are our goals for the end of this lesson. Identify the points of concurrency created by angle bisectors, perpendicular bisectors, and altitudes. Use the properties of these points of concurrency. And then we're going to finish up with something that we'll need later in this unit, solving systems of equations by substitution or elimination. So we'll look at both options there. Now, when we look at a point of concurrency, okay, point of concurrency, three or more lines that have a point in common. Okay, so when we look at these three lines or these three lines, they don't have a singular point in common. They have some points in common of two of the three. So there are some intersections, but it's not a point of concurrency. A point of concurrency needs three or more lines intersecting in an individual point. And we have to understand that segments, planes, rays can also be concurrent if they intersect at a single point. Okay, now, if we have three angle bisectors, so what we've done is we've cut each of these angles into equal parts. Okay, this is a very specific point of concurrency. So if we kind of fill in this chart here, the three angle bisectors of a triangle are concurrent. And the point of concurrency is called the InCenter. Okay, now there's some important properties of the InCenter. You know, these are pieces that we're going to be looking at as we're going through, and a lot of your problems are going to have you identify what type of point of concurrency is this situation. So when we look at the properties of the InCenter, okay, it is an angle bisector of all three angles. The point that they have in common is the center of what we call an inscribed circle. The radius to all of those sides are the same distance. Okay, so this is an inscribed circle. The radius is touching all three sides. Okay, so this circle is equidistant from all three sides of the triangle. The next point of concurrence we have comes from when we have three perpendicular bisectors. So think about what those two terms mean. Perpendicular means that we're cutting the side length in half. Our bisector means that. Perpendicular means that we are crossing at that midpoint at a 90-degree angle. So the three perpendicular bisectors of a triangle are concurrent. Might help if I put an N in it. And the point of concurrency is called the circumcenter. Okay, so when we're looking at the circumcenter, once again, understanding the properties of the circumcenter. Okay, it's the point of concurrency of perpendicular bisectors, so we've looked at that already. It is equidistant from all three vertices. Okay, so the three endpoints that make up the triangle, we have the same distance to all of those points. Okay, so we always want to think about the fact that it is a circumscribed circle. The circle is in some ways on the outside of the triangle, and the circle touches all three vertices. Okay, now, one thing to know, looking at this last picture here at the bottom, the circumcenter may be outside of the triangle when the triangle is obtuse. Okay, so if we have an angle greater than 90 degrees, that's going to push your circumcenter outside of the circle, but we are still equal distance from all three vertices. Okay, so all three vertices fall on the arc of the circle, or that outside radius. So now, let's think about a situation here, and we have to pick what type of point of concurrency that we have. Okay, so we have three cities: Safariville, Maxwell Heights, and Tutstown. So we have these three cities. We want to put in an ice arena that is equal distance from all three high schools. Which point of concurrency should we use? So now, we want to be an equal distance from all three of these points. So if we're going to do that, we want to include the vertices. We want to be equal distance, so we're going to have a center of a circle. And what we have to do is we have to find out how we can make this circle. And my circle isn't perfect, but the center of that circle that goes through all 3 points is the best option. Okay, now what we have to remember about, is this an inscribed circle or is it a circumscribed circle? And in this situation, since the circle goes around the outside of the triangle, this is a circumscribed circle or a circumference, or circumcenter, okay, which comes from the term circumference, distance all the way around the outside of the circle. Okay, now looking at our next situation here. Okay, we've got the city of Bologna. There are 3 roads that make a triangle. Okay, so we've got road number 1, road number 2, road number 3. Okay, so we have the 3 roads, and the mayor wants to put a drinking fountain that is equal distance from all 3 roads. Okay, so we have to be equal distance from the roads, not equal distance from the vertices. So if we want to be equal distance from the roads, this circle has to be inside. Okay, so we have an inscribed circle, and if it's an inscribed circle, this is the best point that we have for this situation, is the InCenter. Okay, equal distance from all 3 sides of the circle is our InCenter. Okay, now last one for today. If we're dealing with the 3 altitudes, okay, remember what an altitude is. An altitude goes from a vertice, and it is perpendicular to the side opposite of the vertice. Okay, so once again, vertice, perpendicular line, so we have opposite reciprocal slopes between the side and the altitude. Okay, the 3 altitudes of the triangle are concurrent, and the point of concurrency is called the orthocenter. Okay, so when we look at properties of the orthocenter, the altitudes or the orthocenter might fall outside of the triangle again when the triangle is obtuse. Okay, just based on how they have to be drawn, we might have to extend a side length, because remember, when we're talking about a perpendicular line, okay, it's perpendicular to the line. It may not be perpendicular to the segment or side of the triangle. Okay, now last piece for today, get us into some of the algebraic stuff that we're going to be working on in this unit as well, is the systems of equations. Okay, when we have 2 line equations, there are 3 things that can happen. They can be parallel. They can actually be the same line, or they intersect at a point. And what we're really going to focus on here is the intersection of the point. Now, if we can graph, it's very easy to see on this graph that the point of intersection is at the point 1, 3. When x is 1, y is 3, and that is a point, and remember, this is what it means to be a point of intersection. It is the one point that works properly in both equations. Okay, so this is the only point in the universe, okay, that works in both of those equations to give us a true outcome, true situation. Now, if we don't have a graph, there are two options for finding the point of intersection. One of them is substitution. Okay, the other one is going to be elimination. We're going to look at both. And when we're looking at substitution, what we want is we want an x equals or a y equals situation. That gives us our substitution situation. Okay, so the first thing that we want to look for is a variable all by itself on one side of the equation. It can be on the left or the right. And there's also the idea of the potential to do this. Okay, but if everything is set up a certain way, we're going to move away from substitution and go right to elimination. Okay, substitution is only a situation that you should use when you identify that you have a variable by itself. Like here we have the x value. So what we know is all of this information is equal to x. So when I look at my second equation, I'm going to take x out and I'm going to substitute with what x equals. So I substitute that into my equation. I'm going to go through and distribute the two. Remember, when you're substituting, you have to substitute into a set of parentheses. We've got 6y plus 14 plus 5y equals 3. And then we have to combine like terms and solve for y. So we're putting our two y's together. They're on the same side for 11y plus 14 equals 3. We subtract 14 from both sides. We get 11y equals negative 11. We divide by 11, and we get y equals negative 1. Okay, so now we have the y equals negative 1. We want to pick the easiest equation to plug that into to get our x. The easiest equation to plug into is the first equation. So we're going to plug in there. We've got x equals 3 times negative 1 plus 7. X equals negative 3 plus 7. X equals 4. Okay, now, once I have these two values, I want to know, are these values the right values? Did I make a math mistake? Okay. To check for math mistakes, what we want to do is we're going to take those two values for x and y and plug them into the second equation. So 2 times 4 plus 5 times negative 1, does that equal 3? And if I get the correct answer here, I know that my point is correct. So 8 plus a negative 5, does that equal 3? And it does. So now I know that I have the proper point of intersection. Points of intersection need parentheses. So it's parenthesis 4, comma, negative 1. Always x before y. So that's substitution method. Remember, substitution method happens when you have a variable by itself on one side. The other option is elimination method. Now, notice in this equation, my variables are all on the left. They can be all on the left, they can be all on the right. Either way doesn't really matter as much. So in this situation, what we want to do is we want to find a point that we can eliminate. So what we're looking for is equal to but opposite. I can make my x's equal but opposite. Okay, easiest way here is multiplying by a -3 with the first equation. So I'm going to multiply this first equation through by a -3, and I have a minus 3x plus, or minus 15y. Let's get our signs right. That's always the important piece here. Equals a minus 12. And then my other equation is 3x plus 15y equals -1. Okay, so now I have equal but opposite x's. I also, in this situation, have equal but opposite y's. So normally what will happen as you add through, one of your variables is going to eliminate, your other variable is going to be left, and that's going to allow you to solve. This is a special situation where both variables eliminate. Okay, and think about what we have left. 0 equals -13. Is that true? No. It's actually a false statement. If it's true statement, 0 equals 0, 13 equals 13. If it's true, then they're the same line. Okay? If it's false, they are parallel lines that never intersect. Okay, so that's just a quick, brief interview back from your algebra days of substitution and elimination method. Thank you, and have a good day.